Hi. We're going to do this in a recorded fashion, and then later on we'll be able to take some questions, and then I'll be able to answer those tomorrow or online later tonight. I apologize for the change in venue here. Uh, in terms of what we're going to be doing here, I'm going to go through what I think are the important topics for the midterm review. And the first thing I want to sort of touch on is the definition of architecture. We're of course covering the whole broad topic of software engineering and in particular software architecture here. And when we talk about a definition of architecture, we're really talking about that ability, the notion of a system of components that are connected through relationships and support a behavior through the interaction between those parts. So you want to take a look at the different definitions and be prepared to give a definition of your own or one that you've remembered, but preferably the one from class. You'll also want to know about the 4+1 view of architecture and what the role of each of those items is in the model, and that is the logical view, development view, deployment view, and process view, and then the unifying use case view. So for example, if I said what are, as part of our architectural investigation, we're thinking about dividing the system up for easier development, we would be talking about things largely in the development view. You'll of course want to know some basic UML for class diagram, object diagrams, or interaction diagrams. The notion of components and packages, which we saw, the ability to label relationships, and the notion of multiplicities. This is all stuff that we've seen in class and the stuff that we've used to deliver the documents in the labs. The main things that we're going to be looking at in the tests are going to be the different topics of the different requirements, the different qualities in our system. And in particular for availability, that's one of our, I guess you'd say, almost an emergent quality in the sense that it combines some others at the same time. But we saw both in both guest presentations and in our example and in our in the examples and also in our air traffic control lab, we're looking for how we detect faults in availability. We're pinging them, monitoring it, looking for a heartbeat, check timestamps to see when things happened. The main ones that I want you to think about are pinging and monitoring and heartbeat, and self-tests, and the timestamp. Those are probably the main ones. And then when we detect that something is unavailable, what do we do for it? We have both active and passive redundancy, which we've seen examples of. The notion of rolling back, getting back to a starting point that makes sense. It doesn't always make sense to, once we've found that something's in a fault condition, to go back exactly to the last moment. It's back to the last point where we believe that we're in good shape. We can retry things sometimes, or we can operate in degraded behavior. So the key ones here are the active and passive redundancy, the notion of having spares in place, rolling back. We can of course ignore the faulty behavior and let it just continue on, and then operating in a degraded mode. Then in terms of reintroducing, we can restart the system and recover from it in that sense and get back and make ourselves available again. We saw the notion of nonstop forwarding, which means basically use the data we have while we're trying to recover, and even though it's in a slightly degraded condition, it's better than nothing. The example we gave of was a DNS server where It's unlikely that the mapping changed, so we'll cache the last result we got back from the DNS server. If we can't get to it, the DNS server will eventually restart, and we'll be able to return new values along the way. So that would be an example that we looked at. The next one is and how we prevent faults, or in other words, anticipate unavailability. We saw that if we can predict that something's going to fail, for example, if we see degrading performance over time, we can say, you know, I think this is going to be a problem. I'm going to rejuvenate, and that's a key term there, rejuvenate this service by restarting it. We might remove it from service altogether. Or if it's not available enough because we can't handle enough transactions, then we can add additional responders in and increase, in essence, the competence set there. Now I'd like to talk about interoperability. We saw that early on because this is the way we think about exchanging information between two components, and it could be something as simple as a very simple Java interface that all operates in the same thread of control, or it can be two components that are in completely different processes, different memory spaces, where the message has to be translated, packaged up, sent over to the other process, and unpackaged, and the message interpreted, behavior executed, and potentially a return value sent back. So we have two key interoperability tactics that we have to worry about. First is being able to find the endpoint of the other object. And so one of the things we have to think about architecturally is, where do the two components live? So we're thinking about the deployment and process model from our 4+1 view perspective, and we have to think about discovering that service, in other words, binding it, and then we need to also be able to manage the interfaces. In other words, where do they live, how do we find them, and once we do, how do we bind them? And so overall, we're thinking about the names, we're thinking about what data is going across, when does the data come back, in other words, is it synchronous or asynchronous, and then how the data is returned, and then finally when the binding of the service occurs. Is it very early? In other words, we know where the service is and we know exactly how to find it. For example, a strongly typed interface. Or is it a very light binding? In other words, we look up the endpoint each time in a DNS server, get the URL back, and then send our request to a web server on the end. So interoperability also depends on the case that we need to know the types, what kind of data is moving back and forth. Things are more interoperable if they are loosely typed and loosely coupled. In other words, late binding, loose typing is the most interoperable, but it can be less safe. Strongly typed, early binding, very safe, but less interoperable. Now, we spent quite a bit of time on performance, and the main things that I want people to think about here in performance are the different ways that we, first of all, measure performance, and then ways that we can improve it. We talked about latency, so you'll want to know what latency is and what jitter is, just like we did in the quizzes. So going back and looking at the quizzes and performance will be handy, and making sure that you understand the correct answers there. So when we look at performance, basically we're talking about how many events can we handle and how quickly can we take care of them. And so there's a variety of tactics having to do with both controlling the demand for the resource and managing the resource. So there's two different components to this. A lot of times we think about managing the resources. In other words, can I have a faster processor? Can I have less overhead? But we can also think about it in terms of reducing demand. We can have lower priority events handled after high priority events. So that's prioritizing events. We can bound our execution times and say our response has to fit within a certain amount of time. So we talked about use cases as a good way of measuring between the time an event arrives in our system and the time the response is completed is basically the time box that we're looking at handling. We can also limit the event response, which is we can only handle so many events at a time. And that's a way of saying, look, I just can't handle anymore. Our queue's full, and I'm going to turn you away. So from an architectural perspective, we have to think about what events are coming in, how many we're expecting at a given point. In other words, what our load is going to be, what our total time to respond to it is, our latency, and therefore what our throughput needs to be. If we can handle n number of events per second, and I need to handle 5n, then I'm going to have to figure out some way of dividing that up among 5 identical copies of our responder, if it's possible to do that. Otherwise, I have to queue events up, hoping that eventually the demand decreases and that I will eventually finish my work. So that's the notion of limiting our response there. If we have multiple copies of our computation, then I can spread out the response. I can also maintain multiple copies of data, that's a caching, and that way I don't have to go back to the same resource to get the data all the time. Of course, that only works when the data isn't changing that often. And we saw examples in the Brainy quotes where it made sense to cache a lot of stuff. A little bit in the montage thing, but not quite as much. Security, we're in the test here, it's going to be more about this division between when we can detect an attack, how we can resist it, how we can react to it, and then recover. A lot of times we think of security in terms of resisting the attacks, but that means that we are assuming that somebody is trying to attack it when we identify and authenticate an actor. We then authorize it to do certain activities, but we will also try and detect an actual attack by saying, it seems like somebody's trying to intrude here because they've had a number of illegal or unsuccessful identity and authentication activities. They are probably trying to break in. Another is when they're attempting to deny service by blocking it, sort of like people blocking the entrance to a business if they're protesting it. They're not actually trying to get in, but they're blocking others from being able to get to that service, and it's a type of security intrusion. We also verify message integrity and make sure, wait, is this even a valid message coming in? If it's not, and it has the potential of disrupting our system, we don't want to let it in. We saw quite a few examples of resisting the attacks by, one, doing the identification, authentication, and authorization, but also encrypting data. We talked about limiting exposure by having just a very narrow entry that we can protect very easily and making it impenetrable around the rest of the system, even to authenticated users, but limiting the access to it. We can also limit access by having the entities separate and having a number of them so that you're having to attack a number of them simultaneously. And then in reaction to it, we can either revoke access, can't do it anymore, or we can lock down the resource. But, and here's an important one that Greg Myers was not able to get to today, it's very important that you inform other actors in the system, whether it's an audit trail or some sort of monitoring software or human actors, because at some point you want to know what happened that caused you to try and react to the attack, and then go into recovery, either by restoring the system back to a known state, and going into then your availability scenarios. So in this case, we detect the attack. That's what's causing us to enter this this process, and then once we've detected it, we resist and potentially react or recover from the event. If we successfully resist it, we don't have to worry about reacting to it. If we successfully react to it, then we don't necessarily have to recover. We talked about cohesion and coupling quite a bit, so you'll want to know the definitions of cohesion and coupling. We talked about the notion of a count as a way of measuring complexity. The main thing to understand here is that we will, when we attempt to increase cohesion, we're trying to get that semantic coherence. In other words, attributes and behaviors that have to do with each other. And so we shrink modules down to more manageable sizes. However, that's of course going to increase our coupling, so we always have this dynamic tension between super cohesive and loosely coupled. So what are our strategies for reducing coupling? The main ones that we looked at were encapsulating and making sure that we don't go off base when we need to go get something unless we absolutely have to. We also looked at using intermediaries so that we're always going to the same place to get an update or to go get some data, so that we're only dependent on one module. And then we also talked about reducing the size of a module, splitting it into smaller parts to make it more manageable. We also talked about deferring binding, and this is our spectrum of binding, where we think about going from very early binding to later binding. The later the binding it is, the easier it is to change things, but it's more expensive and potentially interferes with our performance. Now, when it comes to testability, this is a big thing for our system, our aircraft control system. And what we're trying to do is, as we saw in the example, is we wanted to understand for a test, what we're trying to do is to discover faults by running our tests and finding that the expected results were different from the actual results. And so therefore we're detecting the faults. So you want to know that sort of chain of inference, that fault is a result of a mistake made, and then the fault creates an observable error. In part of our tactics for testing things, you'll want to know about black box versus white box, and being able to understand internal state, that sometimes we need to be able to test the internal state in order to make sure that things changed appropriately, for example relationships or other types of what we call side effects. The role of scaffolding in helping us to set up tests, including the setup and the teardown, and the data that's needed to help us test it. In other words, the standard data that says, well, here's my test data, and I have the expected results from this, and I'm going to compare them to see what my errors are. So I may have to have specialized interfaces that will allow me to get to internal state information or otherwise help with the testing that is not part of the actual production code, but I typically leave it in place so as not to change the behavior of that object in any way. I may have abstract data sources that I use as stubs or proxies, and we also we saw that stubs or proxy objects are a way of simulating the behavior of another object so that we can do development of an object without having to have the whole instantiation in place, that we're making it look like it is responding to messages and returning data back when in fact it is a simulated object, and that allows me to put those together as part of my setup in my scaffolding, execute the tests on the target object, and then tear it back down again without having to use the actual production objects that it's related to. And so we know that from a testability perspective, One, we have to be able to do the unit tests on the individual components and make sure that they have the appropriate response and the appropriate internal changes in state, as well as having the appropriate relationships with other objects that it may depend on for its execution. We can make things more testable not only by having well-defined interfaces and being able to both control and observe that state, but also making them less complex, which is a tactic that we've seen in several of these, by making sure that it's less structurally complex. In other words, I don't have too many dependencies, and to make it relatively deterministic. We didn't talk about that much, so don't worry about that part. It's really just limiting the structural complexity of our system. Finally, I'd like you to know about 4 patterns that we talked about. The notion of layering, and in fact you saw that in Greg Meyer's presentation today. You saw that the layering actually achieved 2 purposes there. One was to hide the complexity of the underlying implementation, so it had successively more lower level and implementation details, but it also served in the role of security, that in order to get down to the next layer, that the security was enforced at that point. So he had the different APIs, the 3 different versions of the API, and then there was a little bit of data consistency or making it normalized, but then that next layer down was for security. So layers can serve several purposes. One is to have successively lower layers of abstraction, but it's also a way of partitioning out responsibilities, like in Model View Controller, or in his case he used it as a way of also controlling security. So there's the notion of the layer pattern, layering modules. There's the Model View Controller, which works at the highest levels of architecture down to the lowest levels of coding, and so you'll want to know the responsibilities of the model, the view, and the controller portion of it and their relationships. We saw the pipe and filter, which makes for it's very modifiable and it's relatively cohesive. Each unit represents a specific type of processing. It has high interoperability because I can plug them together easily, or at least they should be able to plug together easily. For example, in the Unix pipe and filters, it assumes standard in and standard out as ways of connecting them together. The pipe and filter mechanism is great for event processing or event handling, a way of, for example, filtering events as they come in and passing them on down the pipe. We also saw peer-to-peer. That was the last pattern we looked at, and that is where each object is connected to another object rather than going through a central server or a central point of failure. It tends to have high reliability, relatively high security, and fairly high performance. The problem is, of course, I have lots of connections potentially, so greater complexity in the connections and making it more difficult to modify the system. So I've made all of the quizzes available online. There, you can go back. You should be able to see all of the quizzes and the correct answers. So you'll want to review those. The tactics in these different qualities. Then you'll want to know the role of the different views in the 4+1 view of architecture, and of course give a quality definition of architecture. It's always a good lead-in to a topic. Now, as you go through this, if you have questions, email them to me and I'll attempt to answer them a little bit later tonight. And we will also be talking a little bit about it in the lab tomorrow. So I will talk to you then.